This video is a wrap up of the regression analysis material for chapter 7. We started to talk about model assumptions and common violations of the ordinary least squares assumptions when on Tuesday. And I just want to kind of briefly review what we talked about in class, but then make sure we finish covering all of the assumptions with examples. As I told you, the assumptions are based on the error term epsilon, and the residuals give us a lot of information about that error term epsilon. And those residuals, remember, are just the observed values of the response variable minus the value on the trend line underneath this, underneath the observed value. So at the same predictor value, the same x coordinate. We're going to use the residuals to investigate the assumptions through residual plots. So really, once you run the residual plots, all these assumptions, except for one, are detectable in those residual plots. And as I told you, you're going to want to run residuals, and Excel will do most of these for you, not all of them, but we'll do most of these. Excel will definitely create the residuals versus the predictor variable or variables, and we want to look for nonlinear patterns there. And the residuals versus the predicted values. And there we would be looking for changing variability, and the residuals sequentially, where we look at correlated observations. And as I told you, residuals can also detect outliers, although we're working with our customer data, so it should be clean data. And for the most part, we don't have a lot of outliers to deal with. As I told you on Tuesday, you're going to want to plot the residuals on the vertical axis and the predictor variable or predicted values on the horizontal. This is what a residual plot that is not violating any of the assumptions looks like. What you want to focus your eye on in some sense is that the variability, if you were to put a band around these, and I didn't draw that very well, but you want to have that the band kind of capturing the variability above and below the x-axis is the same as you go across the values. And you're not seeing any pattern in here. So the first assumption we talked about was that the regression model is linear in the parameters and is correctly specified. And what I told you for that is you just want to look at the residual plots and see if there's any nonlinearity in them. Any discernible trend indicates a nonlinear pattern. And if that happens, we have to employ nonlinear regression, which is a topic we will begin to touch on. This is actually a huge field, a huge discipline. At Pfizer, the statistical nonlinear regression group is the group I worked in, and we were almost 100 people working at various levels of doing nonlinear regression, everybody with a PhD. So yeah, it becomes a really big field of study, but we're just going to touch on it. And we're going to transform the response and predictor variables is one possible way to deal with this. So the example that I want to start with for this one is a sociologist that wishes to study the relationship between age and happiness. And he interviews 24 individuals and collects their data on their age and happiness. And happiness, probably put together some kind of survey. I'm not sure what kind of instrument he used to get this, but he has a scale of 0 to 100. Maybe he just asked them. So let's look at that data. And where you can find this data in our Brightspace page, if you go to content and come down to the data tab. And in the data tab, this is the regression example data for part 2. So this is what the age and happiness data looks like. And what you're going to want to do here is we're going to run a regression. And I want to just go over the good modeling practices, which is if we're going to run a simple regression, we have one predictor, age, that's going to predict happiness. The very first thing we would want to do is graph that with a scatter plot and see if there is a linear relationship, and possibly also run a correlation on this just to see if there's something worth doing here. So the first thing we could do is we could say equals Correl. And that, as you know, there is a tool in the analysis tool pack that will run correlations in a grid if you have more than one. But if you just have one predictor, here age, and we just want to see if it's correlated with happiness, we can just run with the Correl function in Excel. And we see that we have a moderate level of correlation. And then the next thing we'd want to do as part of our exploratory data analysis, our first steps. So let me just label this. Model good behavior for you. Okay, so this is the correlation. Then we'd want to put in a scatter plot. So we can go ahead and select these two columns and insert a scatter plot here. And we'll bring that over here. And we can add a trend line here real quick. Okay. And right now, this is just what I call exploratory data analysis. I'm going to do this nice and quick. I'm not putting in all my axes. If this is something I were to pull into a technical report, I would fix up this plot and make it look more official, more formal. What I do notice in here is what appears to be a nonlinear trend, although there is a trend that may be kind of going up, the trend line's picking up on it. So I already, even before running my regression analysis, I am a little concerned at what appears to be a little wiggle in here. But let's go ahead and run it. So we're going to go to data analysis. And if you get the blank box, sometimes you have to close it out and reopen it, and that takes care of the invisible kind of blank box that sometimes happens. It's basically your laptop processor is having a hard time keeping up with what you're asking it to do. Or you may just need to reboot your laptop if it happens a lot. You may have too much in your buffer memory. Okay, so I have the little regression box. I'm going to input my Y range. So remember, this is my response variable, which is happiness. I'm looking for whether age is a predictor of happiness. So I'm going to put this in here. And then for my input X range, I'm going to put in my predictor variable here. And I'm going to say, yes, I have labels. And I'm going to select my output range to be right here. And I'm going to come down here to the residuals, and I'm going to select residual plots. And I don't need to do the line fit plots for this one. I'll go ahead and select it because if we had multiple linear regression, you can see where for each predictor you'll get a plot. And I'll show you that in a minute on some other data. Actually, yeah, let me just wait and show it to you in another data. And we're going to eventually talk about here a normal probability plot. And so this will not give us what we need, but it helps set us up. So I'm going to go ahead and click that. All right, so now I'll say okay to that. And my output is a little different than what we were seeing when we were just running regressions. So let's just go ahead and get our windows here a little bit bigger so we can see what we're dealing with. Okay, so overall, our overall p-value is a 0.003, so that's definitely below 0.05, so that's good. In this, there's no model selection going on because we only have one predictor in our data. So we're happy to see that 0.0003 number. We see that there is a positive correlation coefficient implying a positive slope. So implying the older you get, the older these people got, I should say, the happier they report being. The p-value on age as a predictor is matching because there are no more, this is a simple linear correlation. There's no more predictors, so that we're not surprised by that. The joint significance of all the predictors when you only have one is going to match the significance of one predictor, right? Okay, so now that we're looking at this, let's look at the first thing that we asked for. Let's move this, we'll come back to this one later. Let's look at this residual plot. Notice this very, very marked U-shaped behavior. So what we're seeing is a very strong nonlinearity in this data. So we would definitely say we are in violation of that first assumption because we don't want to see anything like this. This looks very different than that graph I showed you of kind of how you really do actually want it to look. Okay. So this is just a slide of what we saw. We saw the original trend in the data, made us a little suspect we might see it. Sometimes if you have a lot of data, you can't actually see this as well. You actually need to see the residuals themselves to see what's really going on. This sort of exaggerates it, if you will. It kind of magnifies the issue. Okay, the second assumption is one we've already talked about. That was that you don't want to have any multicollinearity amongst your predictors. So this is a case when you have a multiple linear regression, so more than one predictor. And it happens if two or more of the predictors are correlated. As we talked about this in class, the ordinary least squares mechanism mathematically breaks down. We want to detect high correlations between predictors to determine if this is what's going on. And then I talked in class about other things that can happen if you forgot to check if they're correlated, or if maybe you didn't realize that they were correlated because maybe one of them is a dummy variable. It's hard to see that with exploratory data analysis. But other things can go wrong. So if you start seeing weird things happening, like everything looks good, but you have an insignificant p-value, you have a p-value that's really high, but it's an important predictor, you know that like logically, and you're like, whoa, something's going on. The remedy is you drop one of the collinear variables. You basically, of your collinear variables, because you could have like 3 that are all related, pick one that you think it makes the most sense. And then at the end, when you have your final model, you're going to swap in the others to see if they improve the fit. Sometimes what you think originally may not be the best choice ends up being the better choice. You can always do these other things as well. And we saw the example in class of this with the college earnings. We saw that debt and grad were correlated in that example. And we tried swapping them out. We ended up going with the grad as our predictor. Okay, the next assumption we talked about in class was that conditional on the values of the predictor, the variance of the error term is the same for all observations. And this just means you have constant variability, and that's that band I was talking about that we want to have across our data. Technically, this means there's no heteroscedasticity. I'm not going to hold you to knowing that word. It breaks down with cross-sectional data. This is what our customer data is. So you usually have time series data or cross-sectional data. So it is something we want to be checking for. And it breaks down if you have variability in the response, even with one predictor variable, which can cause your estimates, your coefficients, that's what the OLS estimators mean. They can be basically incorrect. They could be going in the wrong. They could be estimating not the mean, but off from mean of what the real coefficient should be. Stop correction. The OLS estimators are still unbiased. So that means the estimated coefficients are actually correct. They will, on average, give you the parameter, the overall population level slope or coefficient. The problem is the standard errors are not appropriate. So you can't use the t-test and the f-test that give us the p-values to enable model selection. So what I told you was you want to model, you want to look at the residual plots, and they should be random. And if you see variability increasing or decreasing, it looks kind of like a triangle. You kind of see a triangle or funnel shape in your plots. You have this problem. And there is a correction, there's a way to handle it, but you basically recalculate your p-values using corrected standard errors on something called White's robust standard errors, but we can't do it in Excel. So if we find this, we just have to report the problem. And then for your task 3 work, if this is something you find, you want to report it, you want to talk about it, but you're going to have to proceed without correcting for the standard errors, unfortunately. R, the software language R, has packages that will correct this for you. So the example I want to talk about to show this is the regression model on the some rental rates in a college neighborhood, where the data is looking at the number of bedrooms, the number of baths, and the square footage, and what the rent is per month. So let's switch over to that data. Okay, so this is the rental data here, and we're going to run a regression model, a multiple linear regression model here. And as I told you, we're going to start with some good modeling practices. So we're going to start with doing some exploratory data analysis by running correlations. These are all numerical. So I'm going to go to the data analysis, and go to correlation, and I'll hit OK. I'm going to put in my input range. What's nice about the correlation little tool here is I can select just across the top. And I do have labels in the first row, and I do want to select my output range, which is going to be right here. So I'll say OK to that. Oh, okay, I think we have to convert them to numbers. Okay. And also, just to make life easier to see everything, let's make them all centered. Okay, so we can see we're interested in rent, and we're looking for things that are correlated with rent. So we see all of these are correlated with rent. Unfortunately, some of these appear also correlated with each other. So we see all of these here are correlated with each other. Oops. And so we have that bath and bedrooms are correlated. We're not surprised, right? More bedrooms, you'd want more bathrooms. Also, more bedrooms, you got to put them somewhere, unless you divide a big room and start chopping it up into tiny little rooms. Bedrooms would be correlated with square footage. You'd imagine a slightly bigger apartment. And therefore, because these are correlated, you end up having the square footage appears also correlated with the number of bathrooms. So we see we have some multicollinearity already present. And so for us, this is going to create a problem there. So let's just say we say, okay, we're going to select from these, and we could run some additional scatter plots to confirm that they are multicollinear. So bath and bedroom, I wanted to show you this because this is going to perhaps look a little weird, because these numbers are going up by steps of whole units or half units if you have a half bath. So let's go see what the scatter plot looks like for this. And you'll see that it doesn't look as obvious. So this one needs to have a title, right? On the, let's put access title. So when you put in the columns into Excel, it's the way I did. I put a little rectangle in like this. Excel automatically makes the first one your x-axis. So this is the number of bedrooms. And it's going to automatically put the second one as the number as the y-axis. And it's going to use the y-axis as the title. So if once we set that up, we can use the little chart element. So those of you on a Mac, which is unfortunately almost everyone, can go up here to the trend line, and we're going to add a linear trend line. You could also do it from this little chart elements down at the bottom. Okay, so we can see, we do see, despite that we have discrete data, it's not continuous. We still can see that there's a trend here. And we can do similarly, we can look at bedroom, and I'm going to hold down my control key and click on square footage and see if these are correlated. So we see that they are correlated. I just want to do a scatter plot to confirm it is a linear correlation. I am seeing this correlation. And looks like we're going to need to put some axis titles. So square footage. And versus bedrooms. Again, I'm kind of just making sure I don't get lost when I look at this, but I'm not going to spend tons of time right now fixing all this up to be super formal. Okay, so I'm seeing that there as well. And so then I look at my last one, which would be square footage versus bath, and I'm willing to bet I'm going to see the same kind of thing here. They're all related. Logically, it makes sense to us. Sometimes you'll be surprised that two things might be correlated. And in a way, that's a good thing if you find something you didn't expect, because that means you learned from your data. All right, so let's go ahead and add this last one in. Access titles, number of bathrooms on the x-axis, and square footage. Access, oops, I misspelled that. Okay. Okay, once again, we can quickly add a trend line in here. So we see we are looking at some of these issues. So we would maybe need to think about which one do we want to use in our model. Okay, so assuming we want to perhaps think about that square footage is the one that has the more continuous measure. So this is just a little bit of a modeling guideline. If you really, really cared about how bedrooms predicted it, you could use it, or baths. But if they're sort of like interchangeable, what you may, right now we're looking at these, they're interchangeable. In the end, we'll try the other ones. But square footage has the most, is the one that is more continuous. I mean, this looks like this data is only precise down to the 1 square foot. It doesn't have decimals, but that's still much closer to continuous than beds and baths are. So I would recommend doing that. So we can say multicollinearity. Found. And so maybe what we can put in here is bed, bath, and square footage correlated. So again, what I'm doing right now is I am showing you sort of what I consider good modeling procedure. You go into your data, you're going to do some exploratory data analysis to support what the model you're going to do. If you find multicollinearity, you write it in your Excel file, as well as it's going to go in the technical report. But this is sort of, if someone had to open up your Excel file, they could kind of follow what you were doing, what you were thinking. You're going to have your initial predictor that we have to choose from those three. We can't use them all, as we saw with assumption 2. We can't have multicollinear predictors. So the initial predictor I'm going to pick, as I told you, is square footage. All right. So given that, we're now going to run a regression analysis. So I'll start that right over here. Let's go back to data analysis, and now let's come down to the regression package. And here I'm going to input my rent. Because that's my response variable. And I'm going to input for my predictor. This is a simple linear regression with one predictor, because although we have 3 variables in our data, they're all correlated. So I'm going to put in the square footage data only. I do have labels, and I'm going to set the output range. Let's move this over, put it right here. And I do want the residual plots. And again, I don't need the line fit plot. I'll go ahead and show it to you. And I'm only going to do an example on the probability plots for you on the first one, so I'm not going to generate that. Okay. All right, so let's select this stuff and see if we can make it more easily readable. Okay. So we see that, fortunately, our initial thing we look at is our p-value of the overall significance, and it does. And since with a simple linear regression, it's the same as the p-value on the one single predictor we have. We use the regression statistics in general to compare between different models, with one exception, and that's the R squared. So once we have our R squared, right, this is telling us that approximately 70% of the variability is explained. And approximately 30% is unexplained. And I should have probably done that with the happiness and age one. So here you can see that our R squared value is much, much lower. So what this is telling us is there's a lot of variability in the data that this model does not capture. And part of the reason is it's nonlinear. So this model we should not be running a linear regression on here anyway. So you're not surprised to see that number be so low when you have such a bad model for your data. Okay, so here we see one that's looking a little better. Because I asked to see the residual plot, I'm getting automatically for the observations, I get the predicted rent. So what this is doing is it's going to take the square footage data. So for every value in the square footage, it's going to calculate the rent using the slope and y-intercept. So the y-intercept is $512.98. And for every foot of square footage, it's going to add 55 cents to the rent. So from that, we get these predicted rent values, and you can run that just to check if you want that if you put in 500 for the square footage into the point slope equation of the line, not sorry, points out, y-intercept equation of the line, y equals mx plus b, kind of, with 500 for your x, you're going to get a predicted rent. And then it's going to compare to the residuals, which was 645. So we see that it's a difference of minus 144 of the observed data versus the predicted. And that's where this table of output is generated. Okay, so it's doing all that for you. And then it's going to plot the residual. So it's going to plot all this data right here. Let me grab this graph and put it right next to it. So what it's doing is it's going to look at these residuals and is plotting them against the square footage. So the X values. Okay, and that's the predictor. So let me make it a little bigger. And you can see that we do not have a band that is consistent as we move across. So we're having changing variability here. So we are in violation of the assumption 3. Okay, so if I were to try and draw a band in a way around this variability, first of all, there's not even anything over here, right? And so it's kind of like, boom, that goes up and this kind of goes flat. So we want to have a band around 0 that's the same above and below the axis. So we have this crazy stuff happening here. Yeah, so then you have this one outlier, but number way out here. So there's a lot of weirdness here. This data was not clean coming in. We kind of see that because of this. And it has changing variability, which is not uncommon. So what you can imagine is as the square footage goes up, you may have some apartments that are suddenly, the rent is a lot more, hence high residuals off the predicted. You may also have some apartments that the prediction based on square footage is way too low. I mean, is way too high because maybe they're like dilapidated houses or something. So you can imagine different reasons why you would see that. It makes sense, but it is a problem. So what we would do in the quote real world, where you would be doing this with more advanced software like R, if you saw something like this, you would just have to fix this p-value. And oh, by the way, the p-value, those of you who hate looking at scientific notation, right, you can always switch this to a number. And I do recommend you look at least out to 4 decimals. So yeah, it's very significant predictor, but what's the story with that? We cannot trust the standard error because of this changing variability. That standard error has been calculated incorrectly. So we can't trust this p-value. So therefore, we, in some sense, can't really trust that we found a significant predictor. Unfortunately, for our case, we are going to use this. We're going to blur our eyes when we see this. We're going to talk about it. We're going to identify it. We're not going to hide it, but we are also going to make sure we're not going to let it stop us from building models, unfortunately for us, for our class, because I want you guys to learn how to build models, and this might happen. Okay, so the next thing I wanted to talk about is the other plot that was made, and that was a square footage. So that's the predictor line fit plot. So this is, if you have a single, a simple linear regression with just one predictor, it's going to be the same plot that we did initially for, oops, what happened to it? I got overwritten somehow. No, I did get overwritten. That's weird. Let me do it. Oh, there it was. There it is. Okay. So this plot, where'd it go? Sorry. Square footage. Yeah, this one. Oh no, sorry. We didn't run the original correlation scatter plots. I should have done that. Okay. Once we decided that our initial predictor was square footage, I should have confirmed it was not, that it was a linear relationship. So let me go back and do that. I should have done that up here. All right, so that's, and I'm going to want rent on the y-axis. So I'm going to make a copy of rent and put it right here. And I'll just add a little column to give us a little space. Okay. So the reason I did that is because, like I told you, in Excel, whatever you put in first will go on the x-axis. Our response is rent. We're trying to predict rent, so we want it on the y-axis. So I'm going to go in here and make a scatter plot of that and move it up here and get smaller so it'll fit. Okay. Okay, so this is rent. So rent, dollars. We're not looking for overseas accommodations. And by square foot. All right, and we can put a trend line in here. And we see that it does appear to be a linear trend. Okay, so I should have done that when I identified which was going to be my initial predictor. It's looking good right now. That appears to work. But we ran into this problem with the changing variability. Okay, so one of the things that we could do at this point is try running this model with one of the other predictors, or either better or bad, but they're very likely to have the same issue because they're all correlated. So at this point, we may not be able to fix this, but we can go ahead and try. Oh, I was going to show you what this is. So this plot is basically the same as this plot. What you're seeing in the difference is up here, this trend line is based on the intercept, the y equals mx plus b type, right? The intercept plus the slope times the range of values for our square footage, and that creates the trend line. What this does is very similar, except it only creates a dot. It doesn't create a trend line. It creates a dot for each square footage in our data. It's going to plug it in, and it's just basically plotting these predicted rents right here. So that's showing you that, and you can put a trend line on this. So you can see that line. And it's just a little difference. This one's like pulled out rectangular, so that's why it looks a little different. The numbers are the same. If I kind of squished it up, you'd start seeing it starts looking very much the same. Okay, so that's what's going on with that one. We can just go ahead and try switching out another one. We're not really going to be able to judge, unfortunately, because we're not in R. So I'm going to stop right there. We're not going to really be able to judge because we're not going to be able to trust the p-values. So we're not going to be able to determine if one of the other predictors is going to fit the data better. In Excel, we're not going to be able to. So in some sense, we're going to, if you encounter this when you're working on task 3, use the one that makes the most sense. So as I suggested, the one that's numeric, continuous versus discrete, and or which one makes most sense from a maybe a marketing point of view to Catherine Hill, things like that. Okay, and just write about why if you see an issue like this. Okay. The next modeling assumption is assumption 4 is that the error term should be uncorrelated across observations. And again, this is the kind of thing you see in the residual plots. This can break down with time series data. You still get estimates of the coefficients that are unbiased. So you can trust that slope coefficients. But the problem is because of that correlation in the residuals, you end up having standard errors that are not correctly calculated. And so what can happen as a result is you get, and this one's the real kind of very serious one, if you will, is that it's going to make your model look better than it is. So it's basically going to say you have smaller p-values than you really should have. And the way to know you have this issue is if you have time series data. You plot the residuals sequentially over time, and you should show no pattern. And one of the patterns that sometimes happens that you want to be aware of is that is a violation of this assumption is if you have a sawtooth pattern where you're going up and down. And for this one, the remedy is to correct the standard errors with something called the Newey-West robust standard errors. Again, not available in Excel, but R does have packages to deal with it. Our data, or customer data that we've been working with all semester is cross-sectional. It is not time series. So this is not something we would encounter, but you may see it in other work you do. So I wanted to go through an example of how you would see it. So here's, we're going to look at some data on sales. And the predictors that we want to look at are the advertising and the unemployment rate. So the idea is if unemployment is higher, maybe people don't have the money to purchase our goods and sales would go down. Or if we spend more on advertising, we maybe believe that our sales would go up. So let's go and look at this data. So this is the sushi restaurant data. I meant to tell you that, sorry. That this is the sales at a sushi restaurant. I forgot. Okay, so here is our data and we want to run regression. So again, let's start out with some exploratory data analysis to see if it even makes sense, right? So let's run some correlation on sales, advertising, and unemployment. These are all numerical. So I'm going to, go to the data tab, go to data analysis. I get that, sometimes I have to wait a second because I get that kind of invisible box, but there it is. I want to input my input range is going to be, notice the month data I'm leaving out, okay? It's just giving me the time series stamp, the order of this data. And then for my output, right where I want to be, F2 seems right. Okay, we're good there. So let me say okay. So once again, let's just make this a little easier to read. And this one too. And let's convert this to number. And center it. All right, so we see that advertising is correlated and unemployment is weakly negatively correlated. Okay, so let's check how that looks in our scatter plots. So we're going to look at sales and advertising. And once again, we want to put sales on the right side so that we can get it into the y-axis. So I'm going to just add a couple of columns in here. And I'm going to make a copy of sales and put it right here. And that's just to enable scatter plots the way I want them. So I'm going to select advertising and sales, go to insert and scatter plot. And we see, again, if this was formal, I would fix my axes range. Right now, I just want to see, it does appear there is some trend in there, possibly. I'm seeing a little wiggling. I'm not sure if it's real. Okay, the other thing I want to consider is unemployment and sales. And again, let's go into insert scatter plot. And we'll put that down here. We'll try and put a trend line in here. So we see a slightly negative trend line. Again, there appears to be a little bit of wiggling. All right. So we're not sure if they're going to balance each other out or what's going on. So at this point, what we would do is we would go ahead and run our, they don't appear correlated. So we're going to go ahead and run our model with both of those. So let me go up to data analysis, and I'm going to come down to regression. I'll say, okay, my response variable, my dependent variable is my sales data at the sushi restaurant. And my rectangle of predictor data is the advertising and unemployment data. And I do have labels. My output range is going to be, let me move this out of the way. I'm going to go ahead and put it up here. And I will go ahead and get the different plots here. So let me just hit OK so you can see the difference between these. Okay. Now let me just make some of this easier to see. Okay. All right, so coming over here, we have a significance of 0.003. That's a joint significance. So that means overall, it appears we did find at least one predictor that was useful. And we're looking at the coefficients here and whether or not our eye is going to come over to the p-values on those. And we're seeing that they appear significant. Okay. So what we care about is whether or not we can trust those p-values, right? So because this is time series data, we have to look out for what are called serial correlation in our residuals, right? Now, these observations right here, 1 through 17, this has the predicted sales based on these values, and we have residuals that were calculated, as I explained in the last example. I will review that with you really quickly. The predictor variables. So, okay, let me just go ahead and write this here, right? So the sales, I'll write it right here. So sales is equal to the y-intercept plus the advertising coefficient. Sorry. I got to put a little apostrophe, so it'll say plus. And you don't have to do this. This is just me trying to show you what's going on. The advertising coefficient times advertising, and then plus, and the unemployment coefficient times whatever the, oops, times the unemployment rate. So that's how we're going to get the sales, which are the predicted sales right here. So using this formula is what Excel's doing inside, and it's calculating the predicted sales based on, let me just make this smaller, right? That's an easier way to do this. Oh, yeah, okay, that just messed that up. All right, so it's going to look at the advertising and the unemployment numbers. So the first one will be, it'll put 550 in for the advertising and multiply that by this coefficient. And it will add to that negative 0.68 times the unemployment rate at this record. And it's going to then add the y-intercept, and it's going to come up with the sales for that first month of 28. And it's going to compare that 28.9449, compare that to a sales of 27,000. And then it's going to subtract it and give us the residual. Okay, so you see that the months go 1 to 17, and the observations here were going 1 to 17. So we can actually just plot the observation knowing that this is corresponding to month and these residuals, and then we can see if we have serial correlation in our data or not. So let's go ahead and grab those observations and the residuals, and we're going to do a little scatter plot of those. Here, and you can see, maybe I'll call this residuals over time. And let's give this the x-axis, the primary horizontal. I'm going to put months. Month. I don't, oh, I see up here is where it's got the x-axis tick marks. I got you. Let's see what it did. All right. So let's go in and just notice that this appears to be going up and down, maybe back up. So this kind of sawtooth pattern or up-down pattern is the problem that we were talking about. So we have this issue in this data, so we cannot trust these values right here. So if we can't trust these values, we can't really use them to select a to possibly drop a predictor as being insignificant. We just can't run the hypothesis test on them at all without correcting. And what's inside the p-value, right, is the test statistic, and the test statistic always is the predicted minus, sorry, the observed minus the predicted divided by the standard error. And so the problem is these standard errors are probably wrong. So that's the trickle down effect, is that we probably can't trust these. So that's our dilemma. And in we don't have time series data, but if you do run into time series data, you have to be aware that this is an issue, and therefore you would want to fix the standard errors, recalculate your p-values, and R has packages that will do all that for you. So at some point, if you are interested in continuing to do data analytics, I do recommend you learn R. You will love it once you learn it. Initially learning it is better done in a class. I actually taught myself, and it was a pretty steep learning curve. Okay. So some of these plots, because they're all based on this model, which we don't really know if we can trust or not. I'm not going to spend too much time on them. The only thing I wanted to point out to you is, assuming we did not have that problem, I wanted you to understand what we're doing here. So this is fitting the unemployment percentages in our data. So going back way over here, the unemployment percentages. So it's putting that in, but it's going to go also include in the model whatever the corresponding advertising is on that record, but it can't graph it. If not, it'd have to be a three-dimensional graph. So that's why these points don't appear to be on a line. They are actually on the axis pointing in the unemployment for the unemployment predictor. they're showing you based on these coefficients and that equation that we had worked on over here. This one, let me go ahead and highlight it. They're running that, but what they're showing you is the predicted value that corresponds to the different values of unemployment. And so what you're trying to see is how well did the predicted values match up. So they're looking like they're matching up fairly close. And then you can do the same thing with the advertising line. And you can see there's a little bit of places where it's off, but for the most part, it's not terrible. So even though we have this whole problem with knowing whether we can trust the p-values or not, it appears in general when we're looking at the specific fits to the data that our predicted values are coming fairly close to our sales. I mean, we're messed up in here. There's some seasonality in based on this. There seems to be some seasonality independent of advertising that is overlapped in here. The unemployment does seem to pick up on it a little bit though. Okay. The next assumption is that the error term epsilon is not correlated with any of the predictor variables. And again, this is going to be something you can see in the residual plots. And this tends to break down when an important predictor variable is excluded or variables are excluded. Unfortunately, this assumption may not break down even when you have important predictor variables. And that should have said excluded. So it's something that you really have to have a strong problem. Like you really miss something important for sometimes to be able to detect this. But if it does happen, you can't even trust the estimates of the coefficients. And again, we just find this by looking at the residual plots. And the remedy is to include all the relevant predictor variables or add more variables to your data, to your model. If possible, it may not be possible if you don't have it in your data. Sometimes regression modeling is done with very large data sets with hundreds, if not thousands of variables. So it might be that something important was not included and needs to be added. Let's go look. So here we're looking at this square foot residual plot where this one did appear to be linear, but when we look at the residuals, we don't see a correlation per se. Perhaps there is a little bit of a correlation. So we could like put a trend line in here and see if there appears to be. Maybe it's because it was generated. Should allow me to add a trend line. No, it's not letting me. Okay, we're going to have to regenerate the residual plot. Okay, so we're going to need the square footage next to the residuals. So let me go grab the square footage. I'm just going to copy the square footage right next to the residuals so I can graph this as a scatter plot that will hopefully let me add a trend line. Okay. All right, so we're seeing a very flat trend line, probably because of this outlier over here. I think if we got rid of that outlier, so we, could go in here and find where that outlier is in our data. So we have a minus 600 and something outlier. So it's right here. So let's say I just remove that from the data. So if it wasn't for the outlier, it does appear that there's a linear trend in the data. And so the residuals do appear correlated. And with the square footage, and that implies that we are missing some important predictor variables in our data, in our model. We don't have anything besides bed and bath, and they're correlated with our square footage. We could imagine that that we may be missing important things like the age of the apartment, the condition of the apartment, the location of the apartment. So there's various other things that are possibly missing in this data. And this suggests that we are missing something. I want to make sure you're clear. Sorry, this one right here. Oh, it did finally draw it for me. Good. Okay, I don't know why it wasn't drawing it initially. But now you know also how to understand that a little bit better. But even if I switched out bed or bath, I would still see this in here. And we can't have multicollinearity. So it's another variable that's not multicollinear with square footage that appears to be missing here. Okay. And the last assumption is that the error term is normally distributed. When it's normally distributed, it allows us to build the interval estimates and to run the hypothesis test. If the error term is not normally distributed, then the interval estimates and hypothesis tests are only valid for large samples. So as I've said a few times, more data tends to fix everything. So we're in the age of big data now, and so hopefully this won't become an issue. But if you have a smaller sample, it is something that could happen. One way to know you're dealing with this, again, is those residual plots versus the predictors. And you don't have a similar number of points above and below the horizontal axis. This would mean that the mean of those residuals is non-zero. And we want them to be normally distributed around a mean of 0. Another way to statistically more in depth, if you will, check is to do a normal probability plot. If you remember from your 210 class or maybe another statistics class, a normal probability plot is a way to test if some values are normally distributed. And I'm going to just show you how to do that. Thinking maybe I'm going to do it with the residuals here. So I'm just going to select these residuals. Oh, I need to put that number back in here. So this corresponds, this is going to equal the observed value minus, that's the predicted value. The observed value is the rent on the 39th observation. So the rent there is this value here. And we're going to subtract from that the predicted. So now we get that back. Okay. And now I realize why I couldn't see the trend line. And the reason I couldn't see the trend line is it was right on top of the axis. It was flat. Okay. But if we look at those, if we look at the residuals, we want to see if on average, the average of these is 0. So we could run a normal probability plot on this. But I wanted to run it on the happiness and age because I already ran a normal probability plot. Now this isn't the one we want actually. The one we want is the one based on residuals. So this is just running it on the actual predicted value. Sorry, on the actual observed values of happiness. So those are the values over here, and they're sorted from smallest to biggest to see if the response variable appears normal, which it does because this appears to be on a line. But what we want to check is if the residuals are normal. So we're going to make a copy of these residuals. And I'm going to just put them here, paste the numbers in, and I'm going to just sort these. So I'll say sorted residuals. So I'm going to sort these residuals here from smallest to biggest. So I'll go to the data, to the sort, and I'm going to continue with the current selection. And I want to do those from smallest to largest. And then I'm going to use these percentiles that this saves us a lot of time. So we don't have to go through all the calculating the percentiles for a normal probability plot. By checking normal probability plot, Excel calculated that part for us. So we're going to go ahead and put these in here. Unfortunately, well, it's going to, normally we want to put the sorted residuals on the y-axis. This is going to flip it, but all we care about is whether it's in a line. So let's just do this in the quickest way we can. We're going to see if this lands on pretty much on a line or not. So we see it's kind of sorted those, right? And as we know, we already rejected this model because it was nonlinear. So I'm not surprised this is not exactly landing on a line, but it does bode well for if we did a nonlinear regression that we would probably fix the problem. Okay, let's go back and see. I think that's the last of them. So the last thing I want to talk about is a model building strategy. Now that we went over all the assumptions. The last thing I want to talk about is a model building strategy now that we went over all the assumptions. So the first thing you want to do is identify the numerical response variable and then all the reasonable predictors. You want to use the ones that make economic and intuitive sense from your data. If you think they all might, you also want to run correlations and scatter plots for numerical variables and contingency tables for categorical variables, because you want to determine which numerical predictors are linearly related to the response variable, which dummy variables appear predictive of a response. You want to identify if there's any multicollinearity among the predictors and choose which predictors to start with for model building. So the approach we're going to take, and the reason I call this a model building strategy and not the model building strategy is because this is an active area of research, and there is some potential bias in this, what's called the full model approach. It is traditionally the most used approach, but there are issues, and there's more advanced software that will run all possibilities for you at all time kind of thing. But for us, we're going to start with the full model, which means we're going to put in all the potential predictors initially, except for multicollinearity. And we'll put those in and we're going to see if we get a overall joint significance of F that's less than 0.05. So we know at least something in that model works. And then we're going to look at the coefficients p-values, and we're going to drop the one with the largest p-values. Even if you have more than one, just drop one at a time, because all the new model will have different p-values. So just drop one at a time, and you run the reduced model and compare the goodness of fit and the p-values of the coefficients. And you continue reducing the model until the preferred model is identified. You may get down to 2 or 3 top choices, because perhaps different goodness of fit measures are kind of pointing in different directions. pointing to different models as being a better model. Once you've gotten it down to 2 or 3, then that's when you go back and you swap out some of the multicollinear predictors with their alternatives and see if you improve the model fits. The goal being to finally get down to what you think are the top 3 model choices. And from this, you want to choose your preferred model or your what I call the final contenders. Once you've done that, you're going to check the modeling assumptions to validate that your preferred model or is okay, or if you're just down to like between 2 final models, if you look at the modeling assumptions, you may be able to differentiate between those 2 final models, which one has better residual profiles. So you look at the residual plots, you should have no trends or look correlated, should not have any changing variability, and should not be correlated in time, and should have an even spread above and below the mean. If you're not really sure, you can run that normal probability plot like I just showed you. Whoops. Okay, so that's how you arrive at your final model that then you will use to interpret the coefficients and make predictions. Okay, so let's go back to the sushi model. Actually, let's go to the rental. I think this one may or may not be a good one. I showed you all examples that had problems. So I'm just trying to go back and show you like, okay, make sure you're clear when you get done and you have your final model that it's the coefficients that you're going to want to interpret, as well as make predictions. So you'll use these coefficients, and I showed you with that other, in the other regression file that's on Brightspace, I showed you in there, in the regression example spreadsheet, I included in there a little tool to do predictions for various, when you put in different values for your square footage, for example, or whatever it is you're modeling. Okay, so that's it for this add-on lecture.